Hello YouTubers and fellow hams. Well, here we are in the last of a series on my 630 meter antenna projects videos for a little while. I'm going to do one more video on propagation and operating down the road a little ways after I've had some time on the band, made a few contacts and learned a few more things. But today I'm talking about the other antenna option I had. Now you may recall back from the videos on this magnetic loop back here that there were two things I was going to try. One was the magnetic loop, and that was a success as far as it could be. I mean, it's a very inefficient antenna at these frequencies. I was able to make one on-the-air contact with it, but its efficiency is so low that it's just not radiating much, you know, maybe a couple hundred milliwatts. The other thing I wanted to try was and load up my end-fed wire for 630 meters. Now, 630 meter antennas, wire antennas, there are several popular types. Let's talk about those. Okay, the common types of wire antennas used for medium wave frequencies or lower are single wire antennas. They're not dipoles in that you don't have, you know, a shield and a center conductor lead, a balance system even. They're a single wire, and the other side of the antenna is the radial field at the ground side. Now, most of these antennas will have a horizontal element near the top or at the top, like in this T antenna or this inverted L, an umbrella antenna or multiple top load wires. And the reason being, a short antenna that is shorter than a quarter wavelength will exhibit a capacitive reactance. It'll give you a capacitance at the frequency that you're at. And the horizontal part kind of balances that out and provides a more stable capacitance, as I understand it from my reading. The other side of the capacitor's plate would be your radial field on the ground. And that's your capacitive reactance. And then the antenna has to be loaded with a large inductor at the feed point at the base. And the vertical part of the antenna is the part that radiates. Okay, the horizontal part just provides a capacitance, a capacity hat, to balance against the inductor and make the thing a resonant circuit. Radial fields. This is something I learned in my research here. I always thought of radials under a vertical antenna as providing a better ground plane than the Earth. And at HF frequencies, that's pretty much true. But when you get down to medium wave and lower, the Earth and the ground is a loss. It'll absorb the radiated energy. And the radial field is a shield. It's an electrical ground for the antenna system that shields it from the Earth and reduces ground loss. So radials at medium wave frequencies are extremely important. You want to have as many as possible and as dense a field of radials as possible to minimize ground losses. So that was something that I learned. That's new. John over at NDJ Technologies, I think I remembered that right, told me that. He's been very helpful in my research. Thank you very much, John. So anyway, optimal antennas for medium wave are usually going to have one of these configurations. Now, existing antennas that you might already have for HF, like many people might have an inverted L that they use for 160 meters or 80 meters, they might have a dipole. Many of you might have a dipole. And if you were to short together the shield and center conductor at the feed point down here at the base of the antenna, you would create a single wire T-shaped antenna that would work for 630 meters. So that could be repurposed. Umbrella antennas will generally have multiple sloping ends off the top and then a vertical section. And then of course multiple top-loaded wires are like the older style Marconi antennas work as well. But for repurposing an existing antenna that you have for HF, the most possible or plausible configuration you're going to have is going to be the inverted L or a dipole that you could turn into a T. All right, and then at the base you need to have a lot of radials put out, or some type of a ground plane. The more the better. In my case, I have very little, and I do not have the option to add more because of the logistics of my city lot in my house. But anyway, we'll get to that. So these are the optimal antenna types. Yeah, here we go. This is one particular antenna, but it gives you a general idea. You'd have a large loading coil at the feed point, a flat area at the top to stabilize and maximize that capacitive effect, balancing against the inductance to make a resonant circuit. And there's another example of, say, a T-style antenna that you could put up with some supports, and then just have your feed point down here. Okay, so you need to load it up, and that's where the inductor comes in. There are various types of variable inductors, but the most common type used for these antennas by far is the variometer. And if we go and we look, I found a very nice paper on early radio experiments here, and early variable inductors, and the first, well, here we go, the first of these to be produced would appear to be the Arton-Perry variable self-inductance standard described by Lord Rayleigh in 1886. These early variometers, which were around 1886 to, Rosenthal patented one, and the Amalgamated Radio Telegraph Company produced it in 1907. So yeah, right around 1900, in that area, a little before, a little after, variable inductors were like this. You had an outer coil and then an inner coil on a form that could be rotated within the outer coil, and that was how you'd vary the inductance. That's a variometer. Here's another example of an early one. I found several. Here's a commercial one that was available. Oh, look at that, $4.50 and $4.75 for the deluxe version. Of course, this was the early 1900s, so that was probably kind of pricey if you did that in today's dollars. And so they were used all over the place for variable inductance. And on the 630 meter band, this type of a variable inductor has been the go-to. It's a very simple type of variable inductor, and it can be made with fairly simple parts. So that's what I'm building today. Now, my antenna, my end-fed wire, is 98 feet long. And it starts at my porch, it goes up over my house, above my chimney, and it slopes down to the shed in the backyard. The house and the shed are the only supports on my lot. I have no trees, no tower, nothing. So my antenna situation is about the worst case scenario. And if it works for me, it'll work for you, probably even better if you have a better antenna to adapt. One note on these antennas, that large inductor is going to cause very, very high RF voltages at its output, thousands of volts. So you want to have your antenna wire insulated. You don't want it resting against your house, any other structures or tree branches. You don't want it tied to a tree branch. You want insulators in there. You want that wire stood off, because there's going to be thousands of volts RF on that wire. I did that since my wire goes up over my house and down to the shed. I made these little insulators like this that would allow me to stand the wire off. So there we go. As you can see, I have an insulator keeping the wire away from the edge of the roof where it goes over the roof. Up at the top where it goes over the chimney, I've got an insulator that keeps the wire off away from the metal. And at the back of the house, again, another insulator that the angle's a little weird, but there's about 1.5 inches of gap there between the edge of the roof and the wire. And that goes all the way down, all the way down to my shed, where I've got an insulator at the termination point. So you want the wire to be stood off from structures. That's really important. I saw a Hall of Shame archive on one of the websites on 630 meter stuff, where a guy had photographs of various things that had been burned by the wire. Now these guys were probably pumping a little bit of power into the antenna, you know, 20, 30, 40 watts. I'm pushing about 6 watts out of my CW transmitter, which is just not much, but still, you want to have that wire stood off for safety. Okay, so for the bucket variometer, you'll need a 5-gallon bucket, which you can get at Home Depot or any of the hardware stores. I happen to luck out, and my neighbor threw out one. You'll need some PVC pipe for the inner inductor form and for the shaft that goes through that lets you rotate it. 3 or 4 inch works fine for the internal form. I use some 3-inch pipe, and then 1 or 1 inch or 3/4 inch for the shaft that goes through. It's a very simple construction. And then you'll need about 14 gauge wire, solid wire, for winding the outside of the inductor. I did a lot of filming while I worked on this at the bench, so let's go down to the bench and I'll show you building my bucket variometer. So here's where I'm at on the bucket variometer. Now I could have filmed me drilling and cutting and all that, but you know, hey, cutting with a saw, drilling with a drill, you've seen that before. I figured I'd show you the hardware and some of the details of how I'm building it as we go, and then maybe some of the winding, and then we'll look at the finished product. So this is the bucket, and it is a 5-gallon bucket that used to hold whole kosher dill pickles, or deli pickles. My neighbor threw this bucket out, and I thought, hey, perfect, what do you know? There we go, a bucket. So this one is not as tapered as some buckets, but it is a little bit tapered. It gets a little narrower at the bottom than it does at the top. And I'll talk about how I'm going to wind the wire to deal with that taper. We've got a piece of PVC going through for a handle. Inside of it, you can see the 3-inch piece of PVC that rotates, and that'll be the rotating coil. Around the outside I have put some connectors. It's going to be sitting like this on the porch to keep the critters out. So here I've got an SO239 that will be the coax coming in, and internally that's connected to this binding post so that I can have an external alligator clip for the taps on the first coil. And then I've got a little wire, or a little hole here where the wire will come out and start going around for the winds. And then up here, next to the shaft, I got another wire. That's where this coil is going to end as it goes in there. And then inside, at that point, there's a little grounding lug that wire will attach to. And then for connecting the middle coil here, I've got some 14 gauge stranded wire that'll go from the ground lug here down to that one to continue the coil onto the center form. And then at the other end of then it's just the same on the other side. At the other end of the form, there's another ground lug where the windings will end, which goes over to another one here. And right there's a little hole where that'll come out, and then it'll wind around and around and around and around and around and go in this hole down here where it'll connect to that binding post, and that's where the antenna will connect. I've got a binding post here opposite the SO239, and I'll run a ground wire from the SO239 across to that binding post, and that'll be where the counterpoise wires, radials, and ground rod connect for the ground side. So it's basically just a great big inductor, right, where the middle part of the inductor is on a rotating form. I should pause here to note wiring. Schematically, these two diagrams show you the basics of the variometer. Figure 1 is the one I'll be talking about during the build, where the coax comes in and the bottom of the coil is shared with the ground and the shield, and then the center is tapped a few turns up to allow you to find an impedance matching point. That is probably the more common type and the way you'd want to go, and it's the way I described wiring it during this build video. However, I ended up going with what you see in figure 2, where the coils are just off the center of the conductor of the coax up to the output to your antenna. Either works. The configuration in figure 1 did work for me as well, but probably because of my lack of a good ground radial system and my goofy wire configuration, I couldn't get the SWR down much below 2 to 1. Going with the wiring in figure 2, I was able to get the SWR right down to 1.16 to 1, and it worked better for me. So these are the two possible configurations of the wiring of the variometer. Choose whichever one works for you. It's easy enough to switch between the two. You only have to change the connection at the bottom there where the coax comes in. Back to the build. Now, the trickiest part about this was centering this. The holes in the sides had to be perfectly centered across the middle of the bucket, right? And I did that by utilizing, on the bottom of the bucket, you've got a nice little point there that marks the center, so that's easy. But there's these little reinforcing pieces around the side, and they're an even number. They're an even number, so they're directly across from each other. So you could draw a line from this one right through that center point to this one. So that made it easy to figure out where to put the holes. Well, so it's on this one and this one, so where they were directly opposite each other, and so that pipe can go right through there. So look for features in your bucket like this. These little, yeah, they don't really show up. Maybe they do. They're these little reinforcing pieces, and they're even numbered and they're perfectly across from each other. So that made it easy to figure out where on the side to put the holes and have it line up. The other tricky part is this guy. And I'm going to pull it out of here and give you a close-up, and we'll take a look at this in detail here. So this is the rotating part that goes inside. This had to be cut to where it cleared the sides of the bucket and the bottom and top about, a little over an inch, just so it could rotate without impacting the sides. Finding the center for drilling the hole through there was a little trickier. You can see where I put my marks here as I measured the diameter, and I found the exact opposite sides, and then just traced those down with a straight edge that I put on the edge of it like that, and made sure it was flat that way, and then I could measure down and put marks where the exact center was. So I got that nice and centered there. You need to affix this to the shaft so it doesn't turn. Now it's held pretty well with friction, but right here where one cylinder penetrates the other, you get kind of a half moon or a little bit of a crescent shape there. So right at the sides of that, right in that little pocket, I drilled a hole here and a hole there, and I just take a couple of screws and I put them in those holes, and when I cinch those or tighten those screws down, they lock this sucker in place, so it's not going to rotate on the shaft or spin on the shaft at all. So that's how I'm going to secure that. The ends, I've drilled a small hole, and I got this little piece of steel rod here that's going in as a handle, and that is going to line up, as you can see, with the center coil, so that on the outside of the bucket I'll have an indication of where the coil is positioned, and I'll be able to rotate it 90 degrees. And I'll also be able to draw a line on the bucket there and there, so I'll see the range visibly and be able to put a mark, maybe a couple of marks where the top and bottom of the band are. So that's how I did that piece. And then on the other side, I've got another hole here with another short peg that goes through there to lock that on the outside of the bucket. And I've got one more hole to drill. I got to put this back together, and then on this side of the bucket I'm going to drill another hole 90 degrees out of phase with this one, and that'll be right at the edge of the bucket too, and put another peg in there so that as you rotate this, it stays centered. And the reason I'm putting that 90 degrees out from this one is on the outside of the bucket where the hole is, you've got a slight bit of curvature, right? So that peg, as it rotates in this direction, can move inward just a teeny tiny bit. So what I'm going to do on this side be 90 degrees out. So when this peg, there we go. So when this peg is on that way, where it wants to be out this way a little bit, this peg will be that way, where it wants to be in just a tiny bit. So the two pegs, as they rotate, will shift together, and that way the shaft won't have any slop to it. So all those little mechanical things make a difference. So now I need to, well, that's the next thing I need to do. That's the only thing I got left to do in the hardware, is get this in there and drill that last hole and get that other peg put in so that I can then have this locked in place when I'm ready for it. And that's it for the hardware. All I've got to do then is wind the wire. That is next. Now I have a spool of 14 gauge solid. I also have a spool of 14 gauge stranded. The solid is going to be the coils. The stranded is going to be the interface between the inner and outer coil. So what I'm doing there is the inner coil. Okay, I've got a ground lug here that has 2 small holes in it. All right, so the coil wire is going to start at that ground lug, wind around till it hits this screw, where it's going to then cross over where the shaft is to another screw and continue winding around till it reaches this ground lug. And then from this ground lug to this ground lug in here will be 14 gauge stranded. Now it's kind of hard to imagine it, but when this is in there, at the vertical point, the distance between here and the ground lug will be shortest. And when this is horizontal, the distance between here and that center ground lug will be just slightly longer, equivalent to the offset from the center to that screw. Okay, I don't know if you can imagine that, but if you went from this center point to the coil out here, all right, and you rotated this, if you were going from the center of the shaft to the edge of the coil, you'd be making a cone shape as it rotates around. But since this screw is offset from the center about an inch, the wire, when this is this way, is going to be the shortest distance to that. And when it's rotated this way, it's going to be about 1.5 inches longer, accounting for this offset here in distance and a little bit of increased distance in this direction. Right? You could do the math with trigonometry and probably figure out that precise distance. But what I know for sure is that when it's this way, it's the longest. So when I attach that stranded wire from this lug to that internal lug, I'll have this 90 degrees, and I'll leave just a teeny bit of slack in it in this direction. And then when it rotates this way, there'll be just a tiny bit more slack, but still not too much. And that should minimize the amount of flex on the wire and the wear and tear on the wire. And also, when I reach this point, the wire will be almost taut, and if I try to rotate beyond it, the wire on each end of this thing will be kind of a limit, right? That will kind of limit how far it goes. So I'll feel that little bit of resistance, and I'll know I can't rotate it any further. So that is the basics of the hardware construction. I'm going to get that other hole drilled and start winding the coils. That's the only thing I've got left to do, is do the windings. Oh yeah, I can't move this without it being out of focus. What's really important is that each of the sections, the top section, the coils on the center piece, and the bottom section down here are all wound in the same direction, right? That's really important. So I made my holes in the right spots where the wire is going to come out. So it's going to come out here, it's going to go around clockwise, it's going to go in here. And then on the other side, it's going to come out here, and it's going to go around clockwise, and it's going to end here, right before the binding post. And then this internal piece, I have to keep track of which way it's aiming. I've made some marks in there so I know which way it goes, so that I can also make sure the windings go from the top down in a clockwise direction, so that all the coils are wound in the same direction. If you wound this backwards from that, it would cancel part of your inductance. It'd probably still work, you know, because you'd still be making the same change as you rotate it. You know, you'd be bucking the magnetic fields or not harmonizing them, but putting them in an exact opposition. So it would work, the adjustment would be in the reverse direction, and you'd have less total inductance. So it's important that all of the windings on the outer side and the inner side are all going in the same direction. So you have to pay attention to that when you're doing this. For winding on this thing, now as I said, there's a slight taper to it, right? And the winding is the tricky part, keeping the wires all nice and closely spaced and regular. And a local ham did this, and so I thought, hey, this is a great idea. Double-sided tape. So yeah, double-sided sticky tape. I'm going to put a strip here and over here, and maybe one in the area where the taps are going to be, and then one on this side. So 4 strips on each of the 4 cardinal directions where each of the coils goes of double-sided sticky tape. And I'll do that on here too, right? So as I run the windings around, they'll stick to the sticky tape, and that'll keep the wire in place as I'm winding this and make it easier to wind. Taps, I'm going to have, on the first part of the coil, I'm going to have a tap on the 2nd turn, the 4th turn, and the 6th turn, and that's the impedance matching tap. If you'll recall from the schematic, your 50 ohm coax comes in, you got the ground at one side of the main coil, and then the center goes to a tap point, and then that tap determines the impedance at the coax, and you want that as close to 50 ohms as possible. So there'll be 3 taps here every other turn, and then up on the section here that feeds the antenna, probably in the last 6 turns, I'll tap every other turn and see where that puts me. I might do more taps. I don't know. You're probably better having more taps, more options than less. Because if I have too much inductance, I'll need to bridge from here down to a tap to reduce the inductance and keep going down until I find where I'm resonating on the band. So taps, the way to do those, as I'm winding the wire and I reach the point where the tap is going to be, I'll strip off a couple inches of insulation, and I'll just take that wire and I'll bend it up and twist it around itself, so it'll be a twist sticking out of bare wire, and that'll be the tap point. And then I can just use an alligator clip to clip on a very short lead that connects to the binding post and then clips into a tap, you see. And same on this end. Whoops. The same on this end. I'll be able to just take a really short little piece of wire with that alligator clip and clip onto a tap to find the impedance. So that's how I'll do the taps. Okay, so I'm going to get the rest of this hardware done, get that last hole drilled and a peg cut for it, and then I'm going to start winding coils. Ugh, this is tedious. Eight. I'm keeping count of the turns. Double-sided tape on that side. It's working pretty good. It's holding the wire in place. 9. I'm keeping count of the turns because I'm going to have to match that number of turns on the other side. Looks like I'm probably going to have about 20. Well, I don't know how I would have done that without the double-sided tape, honestly. That was very tedious. But there is the center inductor. And you can see the 2 screws work perfectly there. They just keep that wire nice and steady. It crosses over nice and clean without getting in the way of the shaft. Yeah, this is 25 turns here, 25 turns here for a total of 50 on this 3-inch piece of PVC. So that's the variometer part, the rotating part. And yeah, there it is. So part 1 done. Now I got to wind the big coils with the taps. That's going to be tricky. So I'm winding away on this, and I'm making these little twist extensions for taps where I pull the wire up and I twist it on itself. And these are going to be where my tap points are. I'm putting a tap every 5 turns for a little ways down on here. I know I'm going to need a lot of inductance, so I'm not going to go too much further with the taps. But this is there we go. Now I'm just sort of guiding the wire around like that as I go and turn the bucket. And I got the spool over here sitting on a stand, so when I turn this, it just pulls wire off the spool. And I just kind of guide it press it down over the tape, making sure it's nice and as even as possible, and they're tight. One, I think I'll do one more tap and hope I don't need less inductance than that. Whoo-wee! Sorry for the camera audio again, but hey, it's mostly done. The only mistake I made, which I didn't think ahead, was the SO239 is too close to the start of the windings, so I actually had to push two of these windings a little out of the way so I'll be able to get the shell in there. So yeah, that's a little messy. Not happy with that, but the only option would be to re-drill another hole for the SO239, maybe up here, and redo all that. And I'm so sore and hurting so much from winding all this that I just decided to push the wires a little out of the way so I can hook it up. Maybe it'll work fine. It should work fine. I can't see why it wouldn't. Anyway, it's all done. It's all together. One massive inductor. And when you look inside, you can see that. And these wires are just long enough. One of them actually goes tight when I get about halfway right there, so it stops the coil, so I know where my end stop is just by the stranded wire. I just feel a little bit of tension. I know I'm at half or the minimum inductance, and then that would be full inductance there. So that just rotates. Got a nice handle on there, so I can make really fine adjustments. I haven't shaved the taps yet. I'll do that when I get out there and hook it up to the wires. So I'm going to measure it with the VNA first without any of the taps in use and see where it's at, see where it's resonating. And then I'll have to, it's all heavy, it's a couple hundred feet of wire I think. And after I figure out where it's resonating, then I'll start messing with these taps up here. Tapping from here to this one to that one or whatever I need if I need to move the resonance point. But hopefully it's going to resonate somewhere in one of these points. I'll be able to rotate this and resonate in the 630 meter band. So I've got it built. Does it work? Yes, it does. I hooked it up to my end-fed wire, and fiddling around with the taps, I was able to get it to where I could tune right to the 630 meter band. Tuning, as with the magnetic loop, is kind of difficult at these frequencies. A standard SWR meter is not going to work at these frequencies. Most antenna analyzers are not going to go that low. I have seen a website out there where you can modify the MFJ antenna analyzer to get it to go down to that frequency range. So you could use that. I would definitely recommend using an antenna analyzer to tune your antenna. If you don't have one, you could probably get close tuning by ear with a receiver, you know, listening for the peak as you fiddle with the taps and rotate the inner conductor. But to fine-tune it and get that SWR down, you're definitely going to need something. Some hams do it with, they build an RF current meter, and they measure the current going out to the antenna and then tune it for a peak when they're transmitting. I suppose it might be possible to do it with some sort of an incandescent light bulb, perhaps, and look for peak brightness, or a field strength meter. You could use a field strength meter when you're out there at the antenna, have somebody key down at low power and then tweak it for that maximum peak at the antenna. So there's ways of doing it. I did it with the mini VNA. One nice thing with the VNA is that it has, along with USB connectivity, it has Bluetooth built in, and it has a companion application that runs on your cell phone or tablet and allows you to operate it in the field with its internal battery. So I hooked the mini VNA up to the bucket variometer. I've got it hooked up to my end-fed wire and my limited counterpoise wire system, and I began experimenting with the taps and scanning. I started scanning from 300 kilohertz to 500 kilohertz just to see where it was, and it was a little bit low, so I moved the taps to get it to come up and eventually got it to where it was within the 630 meter band, and I was able to then fine-tune it by zooming in on the VNA app to just the 630 meter band and center it as best I could right around 474.2. Then I came in the house and I hooked the mini VNA up to the end of the coax in here, and I did a scan, and I had to go back and forth a few times, out there and tweak it and come back in, out there and tweak it and come back in. But eventually I got it tuned to where I was happy, and I'll show you the graph here. So here we are, and the markers are at 474.2, and I've got that peak, or that low SWR point, just a little bit up, you know, because this is the area that you're going to operate for most of the common stuff that's going on, JT9 and all that. So that's where I targeted it. And as you can see, the SWR is 1.12 to 1, and the impedance is about 44.6 ohms. So not quite 50, but certainly close enough. This is really good. I'm pretty happy with this configuration now. So how well does it work? Well, I've only been testing for a few nights. I've got a lot more testing to do. I'm going to do another video where I'm going to talk about 630 meter propagation and show you some operating and talk more about the contacts that I've made. I have made a few contacts so far with the end-fed wire and the bucket variometer, and it is working way better than the magnetic loop. But again, the magnetic loop, it was an experiment. You know, it's not efficient. I never claimed it was, but it would be fun to build, you know, and if you wanted to get on the air in an apartment, it would be your option. But for me, this end-fed wire with the vario is the way I'm going to go. I could hear so many more signals. Transmitting, I only have tested with local hams during the day. Conditions are not that great right now. It's the middle of summer. This is the absolute worst time for medium wave work. Winter, fall, winter, early spring are the best times. But right now there's a lot of atmospheric noise, there's a lot of storms, there's a lot of just static from the noise from the sun. The days are long, so the D layer is persistent and absorbs the signal for longer periods of time. You get narrower windows of propagation. But testing it locally, there's a local ham, Tom, KU8T, who's about 10 miles away from me. He's across town. He's on the other side of the city center, right? So the buildings, all the buildings in the downtown area are between us. He could not hear me at all on the magnetic loop. He could not pick up a signal at all. With the end-fed wire and the bucket, he said I was S9 on his receiver. Good, solid, strong signal. So it is getting out, definitely getting out. It's not an optimal antenna. I'm sure it could do a lot better if I had a good radial field and a good vertical element and top flat part. You know, so like I say, it's not a great antenna, but it is getting out. So I am hoping to have quite a few contacts on 630 meters. That test was very encouraging for me. Also, receiving way better. I'm hearing so many signals. I'm hearing guys from many states away, down as far as Tennessee and further south, out towards the East Coast, up towards Maine, up in that area, and out west. There's not as many stations that are active, but I'm hearing them out there. So it's receiving just wonderfully. Because of the narrower bandwidth provided by the variometer and the tuned antenna, the nearby AM broadcast interference is greatly reduced. You might recall from the magnetic loop video that I showed you that you could hear that sound from the broadcast interference when I put the end-fed wire on the Yaesu 817. Totally gone. Nice, clear, just the signals is all I'm hearing now. So it's working. It's working as well as I am capable of doing at my QTH right now. I think it's the optimal antenna that I can have based on what I have logistically. And it works. So it's easy to build. Build one if you have an antenna that you want to try to repurpose, you know, and you want to get down there and listen. If you've built my CW transmitter or any of the other down converters and other options that are out there to get on 630 meters, you can do it. Something like this bucket variometer will let you repurpose one of your existing wire antennas, or will let you put up a fairly simple wire antenna and get on the band. So have at it. Hope to see you on the air, and look for another video down the road a ways on 630 meter propagation with some operational demos of the antenna system. Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.